So last time we were talking about that all these things that CFD is made up of three components. One is your, so last time we were saying that there has to be so there are three components. One is your fluid dynamics, right, and one is your mathematics and another is your computer science. So these are the three things which together go in developing CFD. Now I am taking you to next stage, that what are the basically variables and equations and properties which are associated with real fluids. So just to give you an overview that how exhaustive this whole issue is. Okay. So first thing is that what about the geometrical parameters? When you talk about CFD, you have to talk about position of each cell in space and time. Okay, and remember we are talking about 1 million cells. We should be able to define position as well in space as well as in time. Then we have to know about the shape and boundary of each cell. Okay, it's only then we will be able to define the space of the cell, what is the domain or you part of the domain which is included in the cell. Then we have to define the boundary of the domain. This is all three things required just to know the, you can say, the geometry of our domain. Now let us move ahead. Properties of fluid. Then we have to talk about properties of fluid. There is, we have to talk about velocity of each cell in space with time. Okay. Then we have to talk about temperature of each cell. We have to talk about pressure and density of each cell. Okay. Then equation of state which relates pressure, temperature and density. Of course, this equation of state will be applicable to all the cells having the same fluid, because equation of state is dependent on the fluid. Okay, so long your fluid is same, equation of state will be same for all the cases. Then we have to talk about viscosity, because all these cells are in relative motion to each other. As a result, they are transferring force, shear force on the surface of each cell. So adjacent cells are transferring force on the cell, the main cell we are talking about. So we should know viscosity, which will tell us what are the forces adjacent cells are applying on the cell under consideration. Okay. Then we talk about conductivities, because what will happen, these cells have imaginary boundaries. The heat is flowing from all around in and out of the cell. So we should know the conductivities in all the three directions, right, X, Y and Z, how the heat is flowing in or out of the cell. Then we should talk about heat transfer coefficient on the surfaces. This is on the boundaries of the domain, because heat transfer convection is not there on the cell boundary, it is on the domain boundary. Okay. Then absorptivity and emissivity on the surfaces, right. Again, this is talking about the domain boundary where the radiations are falling. We should know what is the absorptivity and emissivity at the surfaces. Then transmissivity through the cell. For each cell, the radiations are passing through it, part of that is being absorbed and part of it is being transmitted. So, transmittivity as well as absorptivity. Of the cell. Then turbulent kinetic energy. Okay, how much disturbance is there in the fluid? We should know that. With that, another term comes is turbulent viscosity. Now, when the fluid is in churning state, there is a viscosity which comes into play, and that is called turbulent viscosity, which converts that chaotic motion into heat. Same thing like in a laminar flow. Laminar flow also, what is happening? You have velocity gradient which over a period of time normalizes, and the change in energy gets converted into heat. Same thing happens in the turbulent flow. There is a churning, lot of churning. Different parcels of the fluid, they are interacting with each other, applying force on each other because of turbulent viscosity. But also that energy gets converted into heat over a period of time. So we have to talk about that. And then if you are dealing in more number of species than one, then you have to talk about the concentration of each species. So these are the parameters which we have to talk about. Then we have to talk about environmental parameters. What are those? There are external forces such as pressure. Okay, pressure is there between cells also. There can be a pressure gradient throughout the domain. Okay, so each cell would apply force on the adjacent cell because of pressure difference. But at the boundary also there is a pressure difference with the environment. Environment will also apply force inside or outside. I mean, it could be either way depending upon the pressure difference. Then body forces. Now body forces are the forces which apply on the cell due to its volume or its content or mass. So they are forces like gravitation and electromagnetic forces which act on each cell. Right? So if suppose there is some fluid going on, gravity is also acting on each cell. Okay? Then if your fluid is rotating, then you have to talk about centrifugal forces and Coriolis forces. Right? And these first forces come when you take rotating frame of reference. These are imaginary forces, right? If you are talking about inertial frame, these forces are not there. Your Newton equation will as it is apply. You have to not talk about centrifugal force or Coriolis force. But sometimes when you are dealing with rotatory machines, then what happens is that rotating frame system is more adequate to solve that problem. The moment you go for rotating frame of reference, it becomes a non-inertial frame. And then two forces, this Coriolis force and your centrifugal force, they come into play. Okay, come into play in the sense they are not really there. It is the equation which get unbalanced, because what you are doing, you are applying the Newton's law of equation which are valid in inertial frame of reference in frames which are rotating. So whenever you move from inertial frame to rotating frames, you have to take care of this. It's something like that when you are talking about accelerating frame. So there are three types of frame. I can it's better that I come here. So if what is the inertial frame? So you have inertial frame, that is one frame. It is in which u is equal to constant. You have frame velocity which is, तो inertial frame हो गया. उसके बाद होगा you have non-inertial frame. In non-inertial frame, so what I was talking about, inertial frame, then you talk about non-inertial frame, and the third one is rotating frame, right? What is inertial frame? In which you can say u of frame is equal to constant. That is inertial frame, that the frame velocity is constant. Then non-inertial frame, f is not equal to constant, that it is accelerating frame. And rotating frame is one in which omega of frame is not equal to 0. Okay. Now Newton's law apply to this only. Now whenever you are talking about non-inertial frame, what you have to do, you required your equation have to modified and you have to add inertia forces. It's an example of, you can say, example of a lift. If your lift is accelerating up or down, like it is going up or down with an acceleration, you cannot directly apply Newton's law. You have to compensate for this. Okay? But when you are talking about rotating frame, you have to talk about, because omega is not equal to 0, you have to talk about centrifugal force and Coriolis force. Okay, and all these forces, inertia forces and Coriolis force, they are imaginary, but they come into play because you have changed the reference frame. Okay, so this is what I was saying. Now how do I exit it? Okay, so what I was telling you is that we have to take these forces into account. Then there is a outside temperature, we should know that, and radiations falling on the surfaces, that also we should know. Okay, then there are laws of equations, laws or equations. We have to talk about all these three laws: conservation of mass, conservation of energy, conservation of momentum, right? And this will have, conservation of momentum has three components: x, y and z. Okay, then we have to talk about diffusion equation. If there are more than one species, you have to talk about chemical reactions. If there are more species and they are interacting with each other chemically, You have to talk about phase change. If there are multiple phases and they are changing, then you have to take into account the rate of phase change and the heat of fusion or heat of vaporization. Okay. Then we have to talk about equations which govern turbulence. Okay. All these things together make up CFD. So these we are talking about only equations and parameters which are in and laws which are involved. So it depends upon the problem. Some of them may not apply, and in other cases some others will apply. Suppose there are no multiple phases, phase change is out of question. If there is no chemical reaction, you will not talk about chemical reaction. But if there is a flame, burning, etc., you will take chemical reaction into account, right? So all these things are there. Okay. Now, what are then existing approaches to solve the CFD problem, and what is their limitations and advantages? So, solving the problem of fluid dynamics, there already exists two approaches. One is an analytical and second is experimental approach. These two approaches already exist. Before we could talk about CFD. Again, the CFD which I am talking about is a CFD which is based on computer programming. As I told you, numerical CFD existed, theory existed long back. When people found that they cannot solve the equations of fluid dynamics, differential equations, by mathematics analytical methods, then itself they thought about the numerical methods. They knew about the numerical methods to solve differential equations well before. But that science did not go ahead because the capacity of calculation. We didn't have that much of calculation power. So all these approaches are very old. Only thing, CFD is now dominating. Okay. Now, what are the limitations of analytical approach, and what is analytical approach? Analytical approach is that you are using differential equation and solving them mathematically. That is a. Now, what is the limitation is, first is limitation on the domain. That means very few problems pertaining to ideal situations can be solved. The moment the real life problems start coming into play, or you start trying to convert them into equation, differential equation, you can write their differential equation, no doubt, but you cannot solve them. To solve them, you have to simplify. It's something like you take away viscosity from the whole issue. But real life viscosity is there. So you can solve a problem forgetting about viscosity in an analytical approach, but that does not give you the real life solution. Okay, so that is the limitation of analytical approach. Then time. Now analytical solutions have to be done manually, so they will require a lot of time. Then parameters. So only those parameters that are part of the equations can be solved. Because you write an equation, there are certain parameters involved, you will get the solution for them. Okay. Now again, if you want to find out some other parameters, you have to use different equations to find it out. Okay. But what is the advantage of analytical approach? The advantage is that the solution obtained from the analytical approach is close to the real solution if assumptions and approximation are adequately taken care of. What you are getting? The absolute solution provided your assumptions and approximations have been taken care of. Right? And they do not involve any material cost. You just require pen and paper to solve the problem, right? So this is the advantage of this. Then we talk about experimental approach. It has its own limitations as well as advantages. The first one is the cost. Now when you are doing the experiment, the cost of material becomes predominant, something like setting up of the experiment and conducting the experiment. So you have to set up the experiment, you have to conduct it, and both things will require a lot of cost. Material cost as well as human labor cost. Okay. Then time. Obviously if you are going to set up an experiment and do the experiment, there will be time in setting up the experiment and conducting the experiment. Okay. Now feasibility. Is it possible to put everything in experimental form? No. Not all problems, such as impact of nuclear explosion. Now if suppose you want to study nuclear explosion, you can't do experiment on that. Just to study. You can study a nuclear explosion if you have to do the nuclear explosion. But to study the nuclear explosion, you cannot make a nuclear explosion. Right? So that is the problem here. Again, if you talk about the tornadoes effect on buildings, motor vehicles, aeroplanes, suppose some tornado is coming and you want to find its effect on buildings, aeroplanes or motor vehicles, you can't produce tornado on your own. When tornado comes, if you are lucky and if you have things set up in time, you can do the experiment, but that doesn't happen. You don't know where it will come and when it will strike. So again you are stuck up. Then performance of sports people. If they are sportsmen which are into action, how will you study them? How will you put probe on them? How will you take readings on them? At the most you can take photographs. But why all these things are relevant here? Because they can be done by CFD. That is why we are saying that experimental approach is not helpful here. You can study the behavior of a sportsman and suggest him the corrective measures, studying the CFD, using CFD. Okay. But if he is actually doing it, when he is in action, you cannot perform experiments on him. Right? Like sometimes you must have studied about crash studies, vehicles crash studies. You can put a dummy person there and you can. So what you are doing basically, you are approximating a man with a dummy. You are approximating you can say a very complex type of accident with a simple accident, head-on collision. Or really the accident may not take place like that. And you study. And you are actually able to go up to say, let us say 90% accuracy. But still the real life problems are not solved. The real person is not sitting, the real accident is not taking place. Right? So many things happen. Then size. Sometimes the physical size of problem is so large that it cannot be replicated in experiments. We talk about the size. Now if you want to study a ship or an aeroplane, the size itself is a limitation. Okay. Then parameters. Now another problem comes in. Not all parameters at all location at all times can be measured. Now for every parameter to be measured, you have to put a probe. And the point where you want to measure it, you want to put a probe there. But in the experiment, real life experiment, you may not be able to put probe there. You may not have an adequate probe for that. Or the probe may be so bulky or so interfering that your experiment is affected. So again there is a problem here that sometimes because of accessibility of the location, Sometimes because of the distance from the probe, you have to record also data, right? And then sometimes because of the disturbance caused by adding the probe, your study may not be accurate. So this limitation comes in. Okay. Size of the probes, they can also, suppose I put a thermometer in a flow, right? The flow is changed. What do you do? And studying it from the distance, you may not get the accurate data. So you have to think about it. Then there are various parameters involved, like turbulent kinetic energy, density, velocities. It's not always easy to study them. If at a particular location I want a temperature, I want a pressure, the probe cannot be put there, or the velocity meters cannot be put there. So this is the problem. But there are advantages also. The advantages of experimental approaches: if the problem has been captured properly, the solution obtained from the experimental approach is real. You don't have to bother about the calculation errors, whether you have programmed properly, whether you have made any error in the this. That is not the question, right? Whatever, if you have made the experiment correctly, your solution is going to come as the real solution. Okay. So why this computational fluid then? When you talk about computational fluid dynamics, okay, so what you find that due to the complexity of the equation governing the fluid flow, analytical approach is severely limited in its application. That is one problem. And even your experimental approach is limited in it. There are limitations in both. Now, so what is happening is the continued limitation of these approaches on one hand. So over the last so many years, let us say last 30-40 years, these limitations remain. No improvement has taken, some improvement has taken place in experimental science, some in the mathematics, but not some drastic changes have taken place. But on the other hand, there is a continuous development of the computers. The development on the computer side has been very, very fast, swift and significant. So as a result, development of CFD is application ever increasing variety of problems and wide acceptance. So what is happening? The CFD is becoming more and more dominant because there is a lot many changes occurring in computers. So what has happened is computer has overshoot other things, experimental approach and analytical approach. So people have moved towards it. Now, what are the advancement in the computer which has taken place? One is the cost of computers, and the second is the speed and size of the computer. So both things have taken place. The cost of the computer has come drastically down, and on the other hand, the speed and size of the computer has gone very, very high. Not only the speed of the calculation, size of the memory, but the physical size of the computer has also gone down drastically. Okay. So as a result, what has happened? Now, as the people's attention shifted towards CFD, more and more softwares are coming up in the market to simulate larger, more intricate and wider set of problems of fluid dynamics. So what has happened? People have started working on it, and over the last 30 years or so, what has happened? Now CFD is being applied to larger problems, more intricate problems, and a wider set of problems. Okay, the cost of software is going down continuously. Okay, and there are many softwares have come up. Okay, and the reliability of solutions is also increasing with experience. So as people are working out the problems, slowly and slowly they are realizing the problems both in the you can say the solution techniques and their understanding of the CFD. As a result, they are improving upon the solution. So that is why CFD is coming. So what is the advantages of CFD? It offers the ability to solve a range of complicated flow problems where analytical approach is lacking. So wherever you find that analytical approach cannot be applied, you are using this CFD. And what CFD reduces lead times, cost in design and production. Now you can do calculations fast, you can get results very fast. As a result, your design time and production time comes down. Okay? Then CFD presents a perfect opportunity to study specific terms in governing equation. Now you can also study different terms, right? You want to only study density, you want to study only pressure, you want to study temperature, you want to study viscosity, you want to study turbulent kinetic energy, etc., etc., etc. You can study that. It's like that CFD, you can find temperature in each cell, millions of cells. And suppose you want to measure the temperature in million cells, how will you do it? You cannot. You can't put million probes there. But CFD you can do it. Same thing for pressure, velocity, etc., etc. Okay. Many parameters like turbulent kinetic energy and others that cannot be measured directly can be measured during CFD. You don't have probes to measure the turbulent kinetic energy. Or even if you have, they are complicated one. While with calculations you can find out immediately. Then you can study the performance of individual components. Now in an experimental setup, you have to put all the parts of the system together. But here what you can do, you can separate a part, define its inlet condition and calculate the outlet condition. So in isolation you can study a part. You are not governed by what is happening in other portion of the system, right? So that helps. You can individually improve a system. Then CFD can be used to optimize the system because you can you can study off design conditions. Studying off design condition in an experimental setup will be quite difficult. It might lead to chaos, failures, accidents. But what will happen in case of computer? Nothing. So you can study off design condition. You can study alternative designs. If you want to study more than one design, you have to make experimental setup for both the designs. Here you don't have to do anything. You just make another system and solve it. Okay. Then you can change Reynolds numbers, Mach numbers, Rayleigh number, etc., etc., flow orientation, all that you can change and study them. Then CFD can provide detailed information and understanding of flow process such as flow separation, wall temperatures. Now if you have a flow in which flow separation is taking place, experimentally you don't know where the flow separation will take place. You can't put your probe there in advance. You cannot visualize it sometimes it may be opaque. But CFD, you can very well know at what point the flow separation is taking place. Similarly, at what point the temperature is shooting beyond the limit. Now, in experimental stage, if you have not put the probe on that particular point where the temperature is high, you will not know what is the highest temperature there in the system. But CFD tells you in the whole domain, wherever is the highest temperature, it will tell you immediately. So you know immediately where the problem lies. Okay? Then CFD provides a detailed and visual details of the system. Now you can see everything graphically. CFD is also called, there is an acronym for that, it's an acronym also for, in a lighter sense, it is called colorful drawings. In CFD you get very beautiful drawings, colorful output, but that give you a idea that what is happening. Okay, you can see the flow, okay, feel the flow. Then there are things where the flow conditions that are not reproducible, like we have talked about nuclear accident, geophysical catastrophe and biological fluid dynamics. You want to study how the blood flows in a human body, how will you do the experiment, right? And analytically also it is not possible because your flow passage is not uniform. Your blood is a Newtonian fluid, it is not. All that you can study with CFD. Okay, so this. But then there are disadvantages of CFD also. Okay, and that is very important, because what happens is, for the ease of it, we tend to use CFD as much as we can do, and we think that we have solved the problem wonderfully. But there are limitations and disadvantages. What are they? So CFD solutions are for all cases they are not available. For example, multiple phase flow, boiling and condensation, etc. But these solutions are now available. There was a time when this multi-phase flow, boiling and condensation was difficult to solve. Okay, but now these things have come up. Then we talk about numerical errors. There are two types of error. One is called truncation error. Now truncation error happens because I am just giving a small example here. We can talk about it in detail when we come to it later on. It's a, like you see this is the Taylor series, right? And in Taylor series what we have done, we have taken the first term from here and put it here, right? And now what is happening is we are writing a differential term del u by del x in terms of algebraic terms. Okay, we can write a differential term like this, and of course this can also be converted to a algebraic term. These terms which you leave, because a Taylor series is an infinite series and you cannot take all of them, then you are stuck up, you cannot solve. So somewhere you stop. You stop at third or fourth equation, second, third or fourth term you stop. But that error, that the impact of that is there is some error left. This is called truncation error, because you have truncated the equation from here. It is called truncation error. Then there are round off error. That means we have talked about, suppose you have an equation value like v comes equal to 5.234189631. Now somewhere you cut it off. So this value has become approximate, and that you have to do. You cannot go, because this value actually coming is infinite decimals. So this is called round off errors. Normally what happens, the round of errors cancel out. You go to market to buy certain things, आपके 10 पैसे छुट्टे नहीं है. सपोज द बिल आया 10 रुपये 10 पैसे, अब दुकानदार भी कहता है यार 10 रुपये दे दो चल जाएगा काम. नेक्स्ट टाइम व्हेन यू गो द आइटम कॉस्ट इन 90 रुपीज़, सॉरी 9 रुपीज़ 80 पैसा और 75 पैसा, तो वो कहेगा अच्छा 25 पैसे छोड़ दो, या आपने 10 रुपये का नोट दिया वो 25 पैसे आपको वापस नहीं करेगा. तो ये आपस में बैलेंस होता रहता है. कभी आपने 10 पैसे ज़्यादा दे दिए, कभी उसने 25 पैसे ज़्यादा दे दिए, ऐसा कर लिया. तो राउंड ऑफ एरर भी ऐसा ही होता है. कहीं पर आपने वैल्यू कम हो गई, कहीं पे ज़्यादा हो गई. बट इफ़ दैट राउंड ऑफ एरर कीप्स ऑन एडिंग अप in one direction only, especially when you have to square up, you are always a loser. ठीक है? Where the difference is, the sign of the difference is not mattering, it is the square of difference that is relevant. Then what will happen? There will always be error, and it can accumulate. You have to talk about that. Okay. Then when you are making approximations, they are possible of multiple solution or erroneous solutions. Now you'll ask that why approximations? You have to make approximations, especially in case of turbulence. There are no laws to govern turbulence. Whenever you want to solve the turbulence, so the problem is in CFD there is no problem which is without turbulence. I mean, not to the word, most of the problems contain turbulence. And there is no solution, theoretical solution for turbulence. Because what happens, whenever you try to solve the turbulence, you do averaging. And when you do averaging, ठीक है, एवरेजिंग करना पड़ता है. टर्बुलेंस में you lead to averaging, and averaging leads to unknown parameters. The moment you do averaging, you create certain parameters, and you don't know the physics of that. So actually your solution becomes approximate. Now when your solution is becoming approximate, there is chances of multiple solution or erroneous solution. So if we think that CFD is going to give us the exact solution always, no. We have built-in approximation, Baba. We have truncation error, we have round off error, and we have this error of turbulence error. And then you have error in solving the equation also. The methodology, because you are going by approximate methods, you cannot follow the Gauss elimination method. You are jumping from starting point to the end point, not through a defined path. As I told you last time, you are jumping erratically. Of course, in your mind you have the scheme that how will I go, but there is nothing to ascertain that. At the end you might land up, at the end you might land up at a place which is not the real thing. Yes.
सर ये विंडो ओपन क्लोज करवा दीजिए.
5 मिनट हो गए. So this is the thing that is happening with CFD. So there is a note of caution here. I think we will talk about this only and then stop. Another 5 minutes. Okay. So what is a note of caution? A favorable appraisal of CFD thus far does not suggest that it will soon replace the experimental testing. Experimental testing is still a dominant part of CFD, and especially the wind tunnel experiments are still a viable alternative, and the reason being that they exist. You know, earlier aeroplanes were designed using wind tunnels. Wind tunnels came basically to design the wings of the aeroplanes. Now those structures are existing. Experiments setup is there. So you have to only put up a new wing to test it. So that becomes a cheaper and more reliable in the case, because in CFD you might actually have some problem because you are not following the proper mathematics or proper science. But experiment, all these things are irrelevant. You take the, so wind tunnel experiments are there. CFD still remains relatively primitive. Okay, it says that wind tunnels are very effective for obtaining the global information of complete lift and drag of the body and surface distribution. So you put the wing and you get the total, what will be the lift, what will be the drag, you can calculate everything. Of course that can be done by CFD also, but you get it there also. And it is a relatively primitive state of development, and as I told you, the multi-phase boiling and condensation, they have not been properly captured, but they are slowly improving upon them. CFD solution may not always be perfect or realistic, we have to be sure about that. Then numerical errors are there. Then CFD is not free from approximations. For example, we have talked about that in case of turbulent flows, averaging leads to additional variables for which no physical law exists. So when you try to solve turbulence, you make averaging. When you make averaging, you get the unknowns, variables which are not existent and for which you don't know the physics law, and therefore you have to invent equations to solve them. Invent, because your problem solution cannot proceed unless until you have same number of equation as the number of unknowns. Now what you have done is you have added the number of unknowns, but you are unable to add more number of equations. So you have to forcefully add the number of equations, more equations, which are more or less imaginary. They depend, there is no physics law, because physics law you have already taken care of. You have taken care of continuity, momentum, and Newton's law, energy equation, diffusion, combustion, everything you have already taken care of. Turbulence, you have no way because it's a random process. It's something like how the movement of air molecules is taking place in this room. Even if you know the mechanics, it is so small, it is so complicated. When the one molecule strikes with other, which direction it will go, you don't know. And there are millions of molecules, billions of molecules. Right? So really you don't have the equations to solve those parameters which you have created. Okay? So there is a real danger of that CFD may give an erroneous solution. It's a real danger. It's not hypothetical, it's a real danger. Therefore, numerical results obtained must always be thoroughly examined before they are accepted. And that is why validation is an important part of CFD. Those of you who will be following CFD, the first question the person who is taking your viva will ask you, where is your validation? Where is your validation? Have you validated your results? Even in validation, what you do? You design the program, okay, compare the results of CFD and experimental for some case and project it for some other case. Because if you are able to do the experiment for the case which you are interested in, then there is no need of CFD. If you are able to do experiment on a problem which is of your interest, then what is the use of CFD? If you can. So what you do an experiment on a similar case, verify that CFD and the experiments are giving same result within a limit, then hypothetically you extend it to a new problem, assuming that my problems are similar, so my solution will be within the same range. Big if, right? So this is the limitation of CFD, and therefore in CFD experience becomes very, very important. If somebody has to enter into CFD, he should think of devoting his whole life to it, because you grow as you work on it. But if you are thinking that I have solved one problem and I have no CFD, then sorry, you don't know. So that is why that all these approaches become important, because none of them is perfect. So what do? You take help of all of them. You can't discard the analytical approach, you cannot discard the experimental approach, and you cannot discard CFD. They have relative advantages as well as they have relative disadvantages. It's something like that. Suppose you want to go from here to Bombay or USA. Let us say, take example of USA. So you have to travel by bus also, you have to travel by train also, you have to travel by plane also, and you have to travel by foot also. So all those things are valid and useful and important. You can't just skip one, right? You can't say that okay, I will not walk and I will go from here to US. Not possible, right? Or I will not board the bus, I will only go by plane. Think over it. Even when the plane is so important, it is covering largest distance, the bus travel or the train travel is not useless, it is important. It is part of the whole system. Okay, so these things become important. So CFD complements experimental and analytical approach by providing an alternative cost-effective means of simulating the real flow. So it's an addition to that. Okay? Although each approach has its own merits and demerits, they all remain relevant at the moment. Okay? Unless until CFD reaches a stage where it says that I know everything, I am not making any approximation, right? Everything is supported by fundamental laws of physics, then of course, but still that day is very far off. Okay. In the current scenario, with the development of ever advanced softwares and ease of computational method, one is too tempted to rely on CFD entirely. कमरे में बैठे बैठे हो जाता है, बिस्तर में बैठे बैठे CFD आप कर सकते हो, तो you tend to use it, right? However, CFD involves lot of approximation, and there is always a likelihood of the final solution provided by the software going too far away from the real solution. Okay, so therefore one shall not ignore experimental approach completely and instead use it frequently, specifically to ensure that results being obtained by CFD are validated by experiments. You should always be eager to solve your solution experimentally, validate it at least. And this whole thing now is put up in another triangle, that analytical approach, experimental approach and numerical approach, that is CFD, they all are interconnected, they are all important, they are all should be used. Okay, so we'll stop here and